Welcome to this walkthrough of LeetCode problem number 502, titled IPO. In this problem, we tackle the challenge of maximizing profits by selecting projects within specific constraints, using efficient data structures and algorithms. Let's dive in and explore the optimal approach to solve this intriguing problem. In this problem, you are tasked with selecting projects to maximize your capital. Each project has two key attributes: its profit and its capital requirement. The profit of a project is how much you earn once the project is completed, while its capital requirement specifies the minimum amount of capital you need to start that project. Initially, you're given an amount of capital, W, and you're allowed to complete at most K projects. The goal is to select projects in a way that maximizes your total capital after completing at most K projects. However, you can only select a project if your current capital is greater than or equal to its capital requirement. Once you complete a project, its profit is added to your current capital. The challenge lies in deciding which projects to pick in order to achieve the maximum capital within these constraints. The output of this problem is a single integer, representing the maximum capital you can have after selecting and completing up to K projects. Let's consider an example to understand this better. Suppose K equals 2, the initial capital W is 0, and there are 3 projects with profits, 1, 2, 3, and capital requirements, 0, 1, 1. To solve this, we start with W equals 0. We can select the first project, which has a profit of 1 and requires 0 capital to start. After completing this project, our capital increases to 1. This is the first project we've completed, and we still have the capacity to complete one more project since K equals 2. Now that we have W equals 1, we can select the second project because its capital requirement is also 1. This project has a profit of 2, so after completing it, our capital becomes 1 plus 2 equals 3. At this point, we've completed 2 projects, which is the maximum allowed, as K equals 2. Even though we now have enough capital to start the third project, we can't proceed further because of the limit on the number of projects. Therefore, the maximum capital we achieve in this scenario is 4, which is the sum of our initial capital and the profits from the first 2 projects. Let's look at another example where K equals 3, W equals 0, and the same profits and capital requirements are given, but this time, 0, 1, 2, for capital. Starting with W equals 0, we can again select the first project, which has a profit of 1 and requires no capital. Completing this project increases our capital to 1. Now, with W equals 1, we can select the second project since its capital requirement is 1. With a profit of 2, completing this project raises our capital to 3. Finally, with W equals 3, we can now select the third project, as its capital requirement is 2. This project has a profit of 3, so completing it brings our total capital to 6. Since we've completed all 3 projects, which matches the limit of K equals 3, the maximum capital we can achieve in this scenario is 6. The problem also includes several constraints and edge cases that you need to consider. For example, if K is 0, no projects can be selected, so your result would simply be the initial capital W. If all projects require more capital than the initial W, you won't be able to start any project, and again, the result will be W. In cases where K is very large but the number of available projects N is small, you're limited by the number of available projects. Additionally, if all profits are 0, your capital will remain unchanged at W. On the other hand, if all capital requirements are 0, all projects can be started immediately, and the result will depend on the sum of the K highest profits, or all profits, if K is greater than the total number of projects. These scenarios highlight the importance of carefully analyzing the constraints to handle edge cases effectively. To tackle the IPO problem, our goal is to maximize the total profit by selecting at most K projects from a list, given that each project has a profit and a capital requirement. We start with an initial capital W and can only pick projects where the capital requirement is met. One approach we considered is the brute force method, which involves simulating every possible combination of up to K projects. For each combination, we check if the capital requirement is satisfied, add the corresponding profit to our capital, and track the maximum profit achieved. However, this method is highly inefficient because it requires checking all subsets of projects up to size K. With exponential complexity, this approach quickly becomes impractical for larger inputs, as the time complexity can reach 2 to the power of n in the worst case. While simple to conceptualize, the brute force approach is not a feasible solution for this problem due to its excessive computational cost. To improve on the brute force method, we can adopt a greedy approach by selecting the best project at each step. Here, we sort all projects based on their capital requirements, making it easier to filter out those that cannot be undertaken with the current capital. Once filtered, we choose the project with the highest profit among the eligible ones, add its profit to our capital, and repeat this process up to k times. While this approach is more structured than brute force, it has its own inefficiencies. Sorting projects and filtering them repeatedly for each project selection is computationally expensive. Specifically, the time complexity for this approach is k*n log n, as we sort and filter the projects multiple times during the selection process. This makes it inefficient for large inputs, though it is still an improvement over exhaustive simulation. To address the inefficiencies of sorting and filtering in the greedy approach, we can optimize the process further by utilizing heaps. This method uses two heaps to manage project selection dynamically. A min heap is used to store projects based on their capital requirements, allowing us to efficiently filter out projects as our capital grows. At the same time, a max heap is used to store profits from eligible projects, enabling us to quickly select the most profitable project at each step. The process involves first pushing all projects into the min heap. Then, for up to k iterations, we move all projects from the min heap to the max heap if their capital requirement is less than or equal to the current capital. From the max heap, we pop the project with the highest profit, add its profit to our capital, and continue. If the max heap is empty and no projects are available, we terminate early. This approach is much more efficient, with a time complexity of n log n plus k log n, where the n log n arises from heapifying the projects initially, and k log n accounts for the heap operations during selection. The space complexity is n, for storing the projects in the heaps, making it both time efficient and space efficient. After evaluating various approaches, the optimized strategy using heaps stands out as the best solution. By leveraging a min heap and a max heap, we can efficiently manage project filtering and selection, avoiding the need for repeated sorting. This method achieves the right balance between clarity and performance, making it far superior to brute force or sorting-based greedy approaches. The key insight here is that we don't need to sort the projects repeatedly. Instead, by dynamically managing the projects with heaps, we ensure that the selection process is both fast and scalable. The trade-offs are clear. The brute force approach is impractical due to its exponential complexity, and the greedy sorting method, while better, is still inefficient for larger inputs. The heap-based approach, however, is optimal for both time and space, offering a clear and efficient solution. This makes it the most scalable and practical strategy for solving the IPO problem while maintaining clarity and simplicity in implementation. The goal of this problem is to maximize the total profit by selecting up to k projects from a given list. Each project has a profit and a capital requirement, and we begin with an initial amount of capital, W. The key constraint is that we can only select projects where our current capital meets or exceeds the project's capital requirement. To solve this, we start by parsing the inputs, the maximum number of projects k, the initial capital W, and two lists, profits and capital. We then combine the profits and capital into a list of tuples, where each tuple represents a project as capital, profit. Next, we sort this list in ascending order based on the capital requirements. This ensures that projects with lower capital requirements are handled first. To efficiently manage these projects, we use two heap data structures, a min heap to track projects based on their capital requirements, and a max heap to manage the profits of feasible projects. These heaps will allow us to select projects efficiently during the algorithm's execution. To begin, we initialize two heaps. The min heap, called projects_heap, stores all the projects sorted by their capital requirements. This helps us quickly access the project with the smallest capital requirement. The max heap, called profits_heap, is initially empty and will store the profits of projects that are feasible with the current capital. Since Python's heap module provides only a min heap, we will store profits as negative values to simulate a max heap. We also set up a variable current_capital to keep track of our available capital, which initially equals W. The main loop of the algorithm runs up to k times, or until there are no more projects to execute. In each iteration, we start by identifying all feasible projects, those whose capital requirements are less than or equal to current_capital. For each feasible project, we remove it from projects_heap and add its profit to profits_heap. After that, we execute the most profitable project by taking the maximum profit from profits_heap. This is done by popping the top element, negating its value to restore the original profit, and adding it to current_capital. If no feasible projects remain in the profits_heap, the loop exits early as no further projects can be executed. Once the loop completes, we return the final value of current_capital, which represents the maximum capital achieved after selecting up to k projects. There are several core insights behind this algorithm. First, the use of a min-heap for projects_heap ensures that we can efficiently retrieve the project with the smallest capital requirement, enabling a quick check for feasibility. Second, the max heap for profits_heap allows us to always prioritize the most profitable project from the set of feasible projects. Sorting the projects initially by their capital requirements minimizes unnecessary comparisons, as we process projects in the order of their capital constraints. This approach is inherently greedy. At each step, we select the most profitable option available, ensuring that we maximize our capital growth incrementally. This combination of sorting, heap operations, and a greedy strategy forms the backbone of the solution. The primary data structures used in this algorithm are the min-heap and the max-heap. The min-heap, or projects_heap, is responsible for managing the list of projects sorted by their capital requirements. This allows us to efficiently retrieve the project with the smallest capital requirement. The max-heap, or profits_heap, manages the profits of feasible projects, ensuring that we can always select the most profitable project at each step. When we analyze the time complexity, there are three main components. First, sorting the projects list takes n log n, where n is the number of projects. Second, each project is pushed to and popped from a heap at most once, and since heap operations like push and pop take log n, the total heap operations contribute n log n. Finally, the loop runs up to k times, and in the worst case, each iteration involves a heap operation, adding an additional k log n. Combining these, the overall time complexity is n log n plus k log n, making the algorithm efficient given the constraints. Handling edge cases is critical to ensure the algorithm works correctly under all conditions. If k is 0, no projects can be selected, so we simply return the initial capital W. If no projects are feasible at any step, meaning no projects in projects_heap meet the current capital constraint, we terminate early and return the current capital. Similarly, if the profits or capital lists are empty, we return W, as no projects are available to execute. Another edge case arises when all projects require more capital than the initial W. In this scenario, none of the projects are feasible, and we return W. To illustrate, let's consider an example where k equals 2, W equals 0, profits equals 1, 2, 3, and capital equals 0, 1, 1. After combining and sorting the projects, we have projects equals 0, 1, 1, 2, 1, 3. Initially, projects_heap contains all the projects, and profits_heap is empty. In the first iteration, we add the feasible project, 0, 1, to profits_heap, then execute it to increase current_capital to 1. In the second iteration, we add the next feasible projects, 1, 2, and 1, 3, to profits_heap, then execute the most profitable 1, 1, 3, resulting in a final current_capital of 4. This example demonstrates how the algorithm effectively selects projects to maximize profit. To solve the IPO problem, we start by importing the heap library, which will help us manage a max heap for selecting the most profitable projects efficiently. Inside the findMaximizedCapital function, we define our input parameters, k for the maximum number of projects we can select, W for our initial capital, and two lists, profits and capital, representing the profit and capital required for each project. The first step is to combine the capital and profits lists into a list of tuples called projects. This allows us to associate each project's capital requirement with its corresponding profit. Next, we sort the projects list in ascending order based on the capital requirements. This ensures that we process projects in the order of their affordability. We then create an empty list called max_heap, which will serve as our max heap to store the profits of the projects we can afford. Since Python's heap library provides a min heap by default, we'll use negative profits to simulate max heap behavior. We also initialize an index I to iterate over the sorted projects. Now we enter a while loop that runs as long as we can still choose projects, indicated by K. Inside this loop, we first identify all projects that are feasible with our current capital, W. For each such project, we add its profit, as a negative value, to the max heap and increment the index I to move to the next project. If no project is affordable at any point, we break out of the loop, as we can't proceed further. Once we've added all feasible projects to the max heap, the next step is to select the project with the highest profit. Since the max heap stores profits as negative values, calling heap.heapPop retrieves the smallest negative number, which corresponds to the maximum profit. We negate this value and add it to our current capital, W, effectively simulating the execution of the most profitable project. Afterward, we decrement K to indicate that we've used up one of our available project selections. This process continues until either we've selected K projects or no more feasible projects are available in the max heap. Finally, once the loop ends, we return the updated value of W, which represents the maximum capital we've accumulated after completing up to K projects. This approach ensures that we always prioritize the most profitable projects while adhering to the constraints of the problem. Here, we begin by importing the necessary packages and defining our solution class. The main method, findMaximizedCapital, takes 4 parameters, K, which represents the maximum number of projects we can undertake, W, our initial capital, and 2 arrays, profits and capital, which represent the profit and capital requirements for each project. First, we combine the capital and profits arrays into a single 2D array called projects, where each subarray contains the capital requirement and profit of a project. Then, we sort this array based on the capital requirements in ascending order. This ensures that we process projects with the lowest capital requirements first, which is critical for efficiently determining feasible projects as our available capital increases. Next, we initialize a max heap using a priority queue to store the profits of projects that we can afford to undertake. This heap helps us quickly retrieve the project with the maximum profit. We also define a variable I to track our position as we iterate through the sorted projects array. Finally, we begin a while loop that runs up to K times, representing the maximum number of projects we can select. Within this loop, we add all projects whose capital requirements are less than or equal to our current capital W into the max heap. This ensures that the heap always contains only feasible projects. If no feasible projects are found, meaning the max heap is empty, we terminate the process immediately since there's nothing further we can do to increase our capital. Otherwise, we select the project with the highest profit by polling the max heap, and we add this profit to our current capital W. This step ensures that we maximize our capital incrementally by always choosing the most profitable project available. After selecting a project, we decrement K to reflect that we've undertaken one of the allowed projects. Once the loop ends, either because we've completed K projects or no further feasible projects are available, we return the final value of W, which represents the maximum capital we could achieve given the constraints. This implementation is efficient because sorting the projects array takes O, n log n, and the priority queue operations are logarithmic, making the overall approach suitable for large inputs. In this example, we start with the input values where we can choose at most 2 projects, the initial capital is 0, and we are given the profits and capital requirements for 3 projects. The first step is to prepare the data by combining the capital and profits into tuples, resulting in a list of projects where each tuple represents the capital required and the corresponding profit. We then sort this list by the capital required, which helps us process projects in the order of their feasibility with the available capital. At this point, we initialize an empty max heap to keep track of the most profitable projects we can choose, and we set up an index variable to track our position in the sorted project list. Now, we begin the first iteration. Since we can still choose up to 2 projects, we first check which projects are feasible given our current capital, which is 0. The first project, requiring 0 capital, is feasible, so we push its profit, negated for max heap compatibility, into the max heap. The index is then incremented to move to the next project. Next, we select the most profitable project by popping the top element from the max heap, which gives us a profit of 1. Adding this profit to our capital updates it to 1, and we decrease the number of remaining choices by 1. In the second iteration, with the updated capital of 1, we evaluate the remaining projects. Both projects requiring 1 capital are now feasible, so we add their profits to the max heap. After incrementing the index beyond the list, we pop the highest profit, which is 3, from the heap. This increases our capital to 4, and since we have now chosen 2 projects, the process ends. The final capital is 4, which is our output. Here, we examine the case where the initial capital is insufficient to begin any project. We are again allowed to choose up to 2 projects, but the starting capital is 0, and all projects require at least 1 capital to begin. After preparing the data by combining and sorting the projects based on their required capital, we initialize an empty max heap and set the index to 0. In the first iteration, we check for feasible projects, but since none of the projects have a capital requirement less than or equal to the current capital of 0, no projects are added to the max heap. At this point, the max heap remains empty, which means there are no projects we can select. As a result, the loop terminates early, and the final output is 0, indicating that no capital could be gained. In this scenario, we are allowed to choose only 1 project, and the initial capital is 2, which is already sufficient to start multiple projects. After preparing the project data and sorting by capital requirements, we initialize an empty max heap and set the index to 0. During the feasibility check, all 3 projects are evaluated, and since their capital requirements are less than or equal to the current capital of 2, we add their profits to the max heap, negating the values for compatibility with the max heap structure. Once all feasible projects are added, we pop the most profitable project from the heap, which gives us a profit of 3. Adding this profit to our capital updates it to 5. Since we are only allowed to choose 1 project, the process ends here. The final capital is 5, which is the output for this example. To analyze the time complexity of this solution, we can break it down into specific components. First, we sort the projects list based on their capital values. Since the list has n entries, this sorting operation takes n*log n time. Next, we consider the while loop that processes these projects. This loop runs a maximum of k times, as we are allowed to complete at most k projects. During each iteration, we add all feasible projects, those whose capital requirement is less than or equal to the available capital W, to a max heap. While this involves iterating through a subset of the projects list, each project is added to the heap only once during the entire process, contributing a total of n time for this step across all iterations. After adding projects to the heap, we use heap operations to manage the data. Pushing an element into the max heap, which adjusts the heap structure, has a time complexity of log m, where m represents the current size of the heap. Similarly, popping the most profitable project from the heap also takes log m. Since each of these heap operations occurs at most k times, they add to the overall complexity incrementally. Now, let's combine these components to determine the overall time complexity. Sorting the projects list requires n*log n, and the heap operations, where each project is pushed or popped at most once, collectively take n*log en. While the outer loop runs up to k iterations, the dominating factor remains the sorting in heap operations. As a result, the total time complexity is n*log n plus k*log n. Since k cannot exceed n, this simplifies to n*log n. For the space complexity, the projects list itself requires n space to store tuples of capital and profit. The max heap, which holds the profits of feasible projects, also requires n space in the worst case when all projects are added to the heap. These are the 2 primary contributors to space usage. Additionally, the solution uses a small, constant amount of auxiliary space for variables like w, k, and I. This auxiliary space is negligible compared to the space used by the projects list and the max heap. Therefore, the overall space complexity remains n, as the dominant factors are the storage for the list and heap. To put this in perspective, a naive approach would involve testing all possible combinations of projects to maximize capital. Enumerating subsets of up to k projects would result in an exponential time complexity of 2 to the power of n, which is computationally infeasible for larger input sizes. In contrast, the optimized approach leverages sorting and a max heap to efficiently filter and process projects. This reduces the problem to log n time complexity, which is a dramatic improvement over the brute force method. Lastly, let's consider the best, average, and worst case scenarios for this solution. In the best case, all projects are immediately feasible with the initial capital W. Here, the heap is barely utilized because we can directly process the sorted list, though the time complexity remains log n due to the sorting step. In the average case, we encounter a mix of feasible and infeasible projects, requiring heap push and pop operations to manage the selection process. Even so, the time complexity stays at log n. In the worst case, projects have a wide range of capital requirements, causing the heap to grow to its maximum size of n. Despite this, each project is processed only once, so the time complexity still doesn't exceed log n. Across all cases, the space complexity remains O(n), as the storage requirements for the projects list and the max heap dominate the space usage. One of the most common mistakes when solving the IPO problem is misunderstanding how to use priority queues effectively. Many assume that a single max heap will suffice, but this approach falls short because the problem requires managing two distinct heaps. One heap is used to track projects based on their capital requirements, while the other tracks the most profitable projects that are currently available. Neglecting this dual heap strategy can lead to inefficiencies and incorrect solutions. Another frequent error is not sorting the input properly at the start. Sorting the projects by their capital requirements initially is crucial because it allows us to efficiently determine which projects become available as the capital grows. Without this pre-processing step, you might find yourself repeatedly resorting or performing unnecessary searches, which significantly increases the time complexity. Additionally, some solutions fail to account for the capital constraints altogether, selecting the most profitable project without verifying if the starting capital is sufficient. This results in invalid solutions. Lastly, iterating through the entire project list to select the most profitable option during each round is inefficient, especially for larger inputs, as it leads to a time complexity of O(n). Instead, using a heap ensures that project selection is optimized. Another pitfall to watch for is neglecting edge cases. For example, if all projects require more capital than the initial amount you have, or if the number of projects is fewer than the allowed number of selections, your solution could fail without proper handling. These scenarios highlight the importance of writing robust code that accounts for all possible inputs. From an interview perspective, this problem is an excellent opportunity to demonstrate your understanding of greedy algorithms combined with advanced data structures such as heaps. Discussing the trade-off between pre-processing the project list with an log n sort and the subsequent heap operation shows your ability to balance upfront costs with long-term efficiency. Be prepared to reason through edge cases, like handling scenarios where no projects can be initiated or where multiple projects have identical profits. Finally, emphasizing the dual heap approach in your explanation shows you understand the optimal strategy for managing both capital constraints and profit maximization. When studying related problems, it's helpful to look at other LeetCode questions that use similar patterns. For instance, LeetCode 215, which involves finding the kth largest element in an array, builds a strong foundation in heap usage. The IPO problem itself focuses on combining heaps with greedy strategies, while problems like LeetCode 621, Task Scheduler, emphasize how to use greedy approaches with priority queues in scheduling contexts. LeetCode 630, Course Schedule 3, also deals with maximizing outcomes under resource constraints, making it closely related in concept. As for alternative approaches, a brute force solution would involve checking all projects in each round to find the most profitable one, but this is computationally expensive with a time complexity of O(n). Another approach might attempt to use a single heap, such as a max heap for profit, but this often fails to manage capital constraints effectively. By contrast, the dual heap approach is optimal because it balances correctness with efficiency. By sorting the projects initially and then using 1-minute heap for capital and a max heap for profit, the overall complexity is reduced to O(n) log n plus k log n, making it the most efficient solution. Key patterns from this problem are highly valuable for interviews. The use of dual data structures, particularly a minute heap and max heap, is a recurring pattern in optimization problems with constraints. This problem also highlights the importance of pre-processing data, such as sorting, to reduce the search space and simplify subsequent operations. This is a common strategy in constrained optimization problems. Additionally, prioritizing constraints before maximizing outcomes is a critical framework. For IPO, this means ensuring the capital requirements for projects are satisfied before considering profitability. This prioritization framework is widely applicable to resource allocation problems, making it an essential concept to master. Understanding and applying these patterns effectively showcases your ability to design efficient and scalable algorithms. Great job completing this walkthrough of LeetCode problem number 502, IPO. We covered a structured approach to solving the problem using heaps and a greedy strategy, and discussed key takeaways for similar optimization challenges. Keep practicing, and stay tuned for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!